second midterm practice exam, problem 7. Find the force on the sliding bar for the following situation, where we're going to have this one bar that can slide back and forth here along these two rails, and then we're going to run a current through one rail across the bar down to the other rail. So basically we're going to have a battery across this thing. So find the magnetic force, or the force on this bar. So I've already given you a little bit of a hint, right, which is that we're looking for the magnetic force, and we have an expression for the magnetic force. It's this generalization of QV cross B, where QV is basically our current density, and so this is an integral d3x of J cross B. And so now for us, we have current running through a wire, so we're going to want to adjust this slightly, where this integral d3x of J is going to be written as integral dl integral d2x of J, where this is the current I, and it's in the direction that J is flowing, and so we're going to stick that direction onto this dl. Right? And so this is going to be I integral dl, like that. So sticking that back up here, this is going to say that my magnetic force is I times the integral dl cross B. So that tells us what we need to know really quickly, which is we need to find the magnetic field. Okay, due to these currents, we need to find the magnetic field in this region right here in the bar. And so to do that, we are going to use Biot-Savart rule. Biot-Savart rule will tell us what the magnetic field is due to a bunch of little current loops. Okay. The Biot-Savart law, if I were to write it down, which I will, is that the total magnetic field at any point in space is going to be equal to mu naught if I have wires I over 4 pi times the integral, and here we're going to get dl cross r hat over script r hat over script r squared. Okay? So this is the Biot-Savart rule. For us, in this situation, this is actually going to be pretty easy to specify, and so I might choose my coordinate systems like this: z, y, and x. And if I choose some random point here, right, this is my script r hat for that current element, dl. So that's actually pretty easy. Why don't, for simplicity, I set the origin of the coordinate system there at that end, and we need to define this distance here, d. And so d will be the distance between the two wires. It needs to be defined for this problem to give us a solution. So now all we have to do is actually work this out. The first thing I'm going to notice is I need dl and r to not be in the same direction to get a non-zero result. So I only really need to consider the integral along this part of it and along that part of it. I don't have to worry about the integral along the path, because there the r vector, which would be from some point to where it's pointing, is in the same direction as dl. So the cross product, if they're pointing in the same direction, is 0. So that's nice for us, so we can ignore that. So let's get started. Let's figure out how this works. The magnetic field that we're going to write down using the Biot-Savart law can be written now here as mu naught I over 4 pi, and then I'm just going to write it down for these two paths. I'm going to go from infinity to 0 dx I hat, so this is the direction, this is our dl part of it, cross, now the r vector. The r vector in our case, if I look at it here, is going to be negative x I hat plus y j hat, like that, for the case that I'm going along this wire. Whole thing divided by the r vector squared, so this will be x squared plus y squared to the 3/2 power. So that's writing this script r hat over script r squared as script r vector over script r cubed. So that's making that identification. In addition, I have to consider the other part, which is going to go from 0 to infinity dx, again, I hat cross, and now when I consider a vector like that from some current element on the other side, this is going to be, again, minus x I hat, but then minus d minus y j hat. Okay. And so, and again, I'm going to get x squared plus quantity d minus y squared to the 3/2 power. So now we're going to do some nice tricky tricks. The first one is to realize that these are going to contribute nothing, so I don't need to worry about them. The second one is to realize that since I don't need to worry about those parts, this only depends upon x squared, and this is symmetric in x, so I can make this go from negative infinity to positive infinity and divide by 2, right? And same thing here, I can put a minus out front, I can make it go from negative infinity to positive infinity and divide by 2. Going through this then, the other thing to realize is I have I hat cross j hat, so this is gonna, in the end, this part is gonna give me a k hat. I have I hat cross j hat, also going to give the same k hat, so they're going to point in the same direction, and I might as well pull this minus sign out front, like that. So now I have these fancy integrals, but I can notice something a little bit further. If I don't want to do this integral, this is just the magnetic field of integrating along an entire wire, half of that. But I can use Ampere's law to find the magnetic field along an entire wire. And so I could just use half of the result from Ampere's law. And from Ampere's law, we know that, we'll put this down, from Ampere's law, we know that the magnetic field for a wire is equal to the magnitude of the magnetic field for a wire is equal to mu naught I over 2 pi s, where s is the distance away that we are. So we're just going to want 4 pi s, right, because we're half of that. And so the magnetic field along this path is going to be mu naught I over 4 pi k hat, and then I'm going to get 1 over y minus comes out front, 1 over y plus 1 over d minus y. And that's it. And so I can evaluate these integrals, but because of symmetry, I don't have to, and it's much easier to do this. Okay, so now we have B. We just need to plug it in to the force equation to find F. And so that says that the magnetic force is going to be IL, so this is going to be minus mu naught I squared over 4 pi, then we're going to integrate over L. The L is going to be dy. We're going to have j hat cross k hat, that's the L cross B part. And we're integrating from 0 to d, and we're integrating 1 over y plus 1 over d minus y. Okay. So now I actually see a little bit of an issue, right? Because the integral of 1 over y from 0 to anywhere is infinite. Okay, so what I can do here is I can put in a plus some delta d, say that there's some small separation where it doesn't contribute. And I'm going to have to do that here on the top because I would get the 0 on the other end from that guy. And so now this is actually pretty easy. You can do this integral, and so the magnetic force is going to be J cross K is I, so this will be in the negative x direction, or that way. So minus mu naught I squared over 4 pi, and then we're going to get this log. So we're actually going to get two of them, so we might as well make this a 2. Log of capital D minus delta D over delta D. And so we're going to get two of those, one from that one from that one. They're going to give the exact same thing, which again you could tell because of symmetry. And this is in the I-hat direction. And so that is the force acting on that wire. And the infinite part of things, you can see what it's saying is if I have a little bit of current here, I have this 1 over r squared part of the magnetic field. It's just infinitely strong as I get closer and closer. So realistically, you're gonna have stuff break down before you get to that limit. And so this is putting in this cutoff by hand.